Okay, well, it's really a delight to be here. As was mentioned, I'm Warwick Bowen. I'm from the University of Queensland, and I'm the director of the new ARC Centre in Quantum Biotechnology. And today I'm going to tell you a bit about what we're doing and how it relates to energy. I'm going to give a specific example of some work that's happening in my lab that I hope will be interesting to you. So before I start, our centre, many of you will know what an ARC centre is, but for those of you who don't, they're centres funded by the Australian Research Council for 7 years, and they're national centres, so ours has 5 nodes: UTS, Flinders, UQ, Melbourne, and University of Wollongong. And the aim of the centre is to take quantum technologies, specifically quantum computing and quantum sensing and imaging technologies, and apply them to better understand the life sciences, apply them into the life sciences and applications from the life sciences, ranging from agriculture to energy, pharmaceutical development and health. How does this relate to energy? Well, there are many ways that biotechnology relates to energy, and we've heard of some of them already in the conference to date. Here I'm giving you some examples. So battery chemistries, improved battery chemistries, photosynthesis, we've heard a lot about this morning, understanding how to produce agricultural products more efficiently, green energy, green fuels, and the last one down here on the bottom left, I guess I have a pointer, yes, is we can learn a lot if we can better observe and image biological systems about how they go about getting the best value out of the energy that's input to them. Gerard talked this morning about AI and how machine learning takes so much energy now, but we've got an amazing computer in our head that's able to do very powerful calculations with 100 watts of energy. So understanding how it does that may shed light on machine learning and improve energy efficiency in machine learning. Okay, now I'll move on to the specific example area that I wanted to talk about, and this is the challenge of understanding how proteins work, understanding how they function. So proteins are very important. Essentially every process in your body is driven by motor molecules and enzymes doing stuff at nanoscale. This is an example of one. It's an ATPase molecule, which is the molecule that basically creates the energy in your it produces ATP in your cells, which is the energy that your cells run off. And we know a lot about how proteins work, but there's still a great deal that's not understood. And the reason for that is twofold. It's partly because our simulations simply aren't good enough. So if you want, these are big molecules, they have tens of thousands of atoms. If you want to model them, and they're interacting with their environment in very complex ways, and if you want to model them, you have to make approximations. And that means that oftentimes the models are not predictive. You can explain why something happens after you see it, but it's difficult to predict in advance that it will happen. On the other hand, if you want to see what proteins are doing, then often you make ensemble measurements, and often you measure the coherent response of those molecules to a stimulus, rather than measuring the native response of the proteins to their environment. And that means you're averaging over really important dynamics. So in an ideal world, you could watch as this molecule steps around. It's making these, you can see it stepping, going through an enzyme cycle, and producing ATP. You'd like to be able to watch that and watch it produce ATP, and then be able to control how it interacts with its environment, switch on and off certain interactions to see what that does to the molecule. Currently, our best tools to do that use fluorescence. So they'll take a fluorescent label, which might be larger than the protein or similar sized, and they'll attach it to it. And they're very sophisticated experiments, which end up being slow because fluorophores can't produce many photons per second, and suffer bleaching and other problems. And you have to question whether you're really getting information about what the molecule would do in its native state when you change it. Alternatively, you can genetically engineer the molecule to change its structure, which changes how it interacts with its environment, and see what happens. But then you have to worry about what other things you're changing when you genetically engineer the molecule. So the goal here is to develop experimental tools that allow you to see molecular dynamics faster, at the sort of timescales that we're able to simulate, and to control those dynamics in situ with a single molecule, and do all of this without any labels, which is a difficult task. Okay, I want to give you one example of why you might care about this, and that is agricultural production of ammonia-based fertilizer. This is a really big industry. It's something like $100 billion. And it uses 1% of world energy and 4% of world methane. And it's crucial for our well-being. If you cut off fertilizer supply, bad things happen. All ammonia production is currently based on the Haber-Bosch process. It's a 100-year-old process. It uses very high pressures and very high temperatures. This is why it's energy costly. But we know that there are better ways. So we know that plants just happily make ammonia at ambient temperatures and pressures, and they do this through these bacteria that sit in these little nodules. And those bacteria have within them nitrogenases, which is the enzyme that does the work. We know they can do it. We don't know how they do it. And in fact, in general, if you take a natural enzyme, it can accelerate reactions by 15 orders of magnitude. But if we try to engineer an enzyme to do the same thing, we fail miserably. You might get a factor of 2, you might get a factor of 10, you get nowhere near what nature can do. So we'd like to understand this, and hopefully if we understand it, we can engineer it, and then we can change how you do agricultural industrial production of ammonia. And you might think it's crazy to use enzymes for mass production of a chemical. We already do this. We do this with mental block. Acrylamide, that's what I'm looking for. We produce acrylamide using enzymes now. It's the standard way to produce acrylamide. It is a chemical that you use in making plastics and paper. It's used for water treatment and many other things. So it's not a pipe dream. Okay, so good. How are we going about this in my lab and in Cubic Center? Well, we're using work that's recently been developed in the field of quantum optomechanics. In quantum optomechanics, you use the radiation pressure interaction between light and a mirror in a cavity to control the state of that mirror, right? Or to control the state of the light. And what has this got to do with molecules? Well, the vision is that you can replace the mirror on a spring with this, it's got messed up a little bit, with the vibrations of a molecule. And that means that you may be able to observe very precisely and quantum control the vibrations of that molecule. And at the same time, the molecule interacts with the light in the cavity, and that interaction is Purcell enhanced. So you can hope to do an extremely fast measurement of molecular dynamics and connect that measurement to function, and by controlling the environment using the cavity, understand what the environment does to the function. So that's the idea. What could you do with this? Well, if we just have to look at the quantum optomechanics literature, one thing you could do is laser cooling of the vibrations to the ground state. This would be really nice if you could watch an enzyme stepping, watch it function, and then freeze out a particular vibrational mode of that enzyme. You could understand what that vibrational mode does to the function of the enzyme. But you can go further than this. We know, and Tien gave a really nice talk a couple of talks ago, that we can transfer quantum states from light to material systems or to gigahertz frequencies, and that's a basis of quantum internet or other sorts of quantum state quantum technologies. So one could imagine, and it turns out the best way we currently have of doing these state transfers is using optomechanics. You have a radiation pressure interaction between light and mechanical motion, and then a radiation pressure interaction between microwaves and mechanical motion. So you could take a quantum state of light and imprint it on to the vibrational modes of a molecule, and then ask, what does that do? We had a recent paper come out that I'm referencing here, which shows that there is a very easy way to do quantum state transfer. Very easy, I say in quotation marks. None of this stuff is easy, but significantly drops the experimental requirements for quantum state transfers. And essentially what we show is if you just do feedback cooling, if you detect the position of this mirror with light and you feed that back and apply a force, then that can allow you to transfer quantum states. And they can be interesting quantum states. This is, of course, a Schrodinger cat state or a Fock state or a coherent state. And one might aim to do these sorts of experiments with a molecule at room temperature and with really, really low quality mechanical vibrations, which are typical of a molecule. Now that all sounds, I hope that sounds really hard, because it is. But we've been working pretty hard to get there, and I can't tell you we've got there yet, but I can tell you we're making really meaningful steps. So the big challenge is, how do I get a strong enough interaction over the right timescales with that molecule in a cavity? And the solution that we have come up with is to use a photonic crystal cavity. So this is a cavity that Igor, I should have acknowledged the people who really do the work. This is my postdoc Igor's work. It's a silicon, 1D silicon photonic crystal cavity, which gives us a very high optical quality. We can store light for a long time in it. And then here we have a gold rod, which is plasmonic, and that gives us an intense hotspot. In fact, two intense hotspots, one on either side of the rod, which are of a similar size to a molecule. And the idea is you put a molecule in here, and if you believe the numbers, you can do coherent control, quantum control of molecular motion. We take these cavities and stick them on the end of an optical fiber, and then we dunk them so light can come in and out, and we literally dunk them in a little sample tube that has molecules in it. And where are we at with this? Well, we can see molecules, we can trap them. I believe it's the first time anyone's trapped a molecule, a single molecule, in an optical cavity. We can hold them there at around here, and we can measure their motion super fast. So we can measure the motion at sub-microsecond speeds compared to about 1 millisecond with fluorescence. So we're making really big steps. I hope that we'll have some exciting stuff coming out on the archive soon on this. I wanted to finish my talk by talking about a collaboration which I hope will demonstrate to you why I'm very excited about this stuff. And that was a collaboration with Michael Mayer's group. He's at University of Freiburg. And basically we wanted to get started on the idea of using per cell enhancement to improve measurements of enzyme dynamics while we were doing our development of these high Q cavities to do control. And so he's got these beautiful double nanoholes, which are a plasmonic nanohole that has a bright spot here, and he traps molecules in the nanohole. And we've this is all his work really. The contribution from my lab has just been doing the modeling and prediction and theory associated with it. But this is the sort of thing we can see. So this is a measurement of the transmission through the nanohole when you put a citrate synthase enzyme inside it. And what I think is you're not going to appreciate this until I explain it, but maybe some of you will. Maybe I shouldn't assume, but you're mainly quantum people, right? But what you're seeing here are discrete steps as that enzyme does its thing. Each one of them is a different conformational state of the enzyme, and we can watch it in real time with high bandwidth, with no labels. taking these steps. That's never been possible before. What's more, and we've done this for multiple enzymes, right? But what's more is on this particular enzyme, we see 5 very clear conformations. The theory, the expectations in the field, the understanding of how this molecule works in the field is that there should only be 3. So we're already overturning the decade-long standard knowledge of the field of enzyme dynamics with these sorts of experiments. I could talk some more, but instead of that, I will stop and open for questions, and don't want to get in the way of anyone's lunch. So thank you. Yeah.
I guess they're quantum jumps you're seeing there.
No. They're not quantum jumps.
What are they?
These are not.
They're not quantum jumps. They're jumps in the conformational.
So the way that an enzyme works is it's got this complicated energy landscape with different conformation, sort of minima of energy, which it's sort of stable conformations. And and the environment drives it. And it finds ways to hop through those minima and perform a useful function. And
so you're looking at the shape changes.
And we're seeing the shape change.
Okay. So my question is there any way to feed back on it and prevent it, or change the rates of transitions and then take it out and examine it?
I believe so, and I don't know, right? But I believe so, and so the hope that so there's an interesting question there. Could you could do active feedback? I bet you could do active feedback. I hadn't thought about that before, but like Hiroshi does with quantum control. I mean that would be amazing if you just did feedback to the intensity of the laser and change the trap stiffness and see if you could suppress or amplify or enhance a transition. Love to do that. I'd thought about using optomechanics too, because it's thought that the mechanical vibrations of the molecule drive some of these stepping processes, and so we can amplify them. We could suppress them. We could probably amplify particular paths that get you from one conformation to another. So that's the path I'd thought. But maybe a more direct path is just apply feedback. Yeah.
I'd like also to ask you a very quick question. So I think that the people that introduced is really amazing, and I was wondering if he's able to follow rapid changes of conformation, like those that can add photo switches and photo recognition processes.
So a big part of the goal is to go from the millisecond timescales of fluorescence to nanosecond timescales of most microsecond and nanosecond time scales of most conformational dynamics. So far in our experiments, we've shown we're able to make measurements at 100 nanosecond speeds. That's the fastest anyone's ever measured dynamics of a molecule. As far as I should caveat that there are ensemble type measurements and average measurements, but on just watching the molecule in real time, I think that's the fastest that's been done. And there's femtosecond experiments, but that's fast enough for a lot of conformational dynamics. I think we will push that another 2 orders of magnitude, so we'll get to about 1 nanosecond. Getting beyond that might be difficult, but I'm not sure.
Thanks for your talk, Warwick. Just a quick question on the photonic crystal on the end of the fiber. Just wondering, how mechanically stable is that?
Good question, and it depends a lot on the application. So the question is I guess if I rephrase the question, it would be, how often does the cavity break off the fiber?
Sure, or even in measurement, does that affect it?
So for whatever, so we've actually put a lot of effort into understanding the best ways to attach the cavity to the fiber. We've got a technical paper on this, which people might find useful, because one of my poor students went through and just tried every type of glue known to man and every type of processing, and then tested how stable they were. So for some applications, that's important. It turns out for this application, Van der Waals force is enough, and it seems like everything's really stable. So we don't even use glue at all.